Modeling of Tangential Teff Threshing and Separation System. Abstract: teff is a small-size cereal that has its origin in Ethiopia. It is the major cereal grown on about 3 million hectares annually, which equates to 27% of the land. 70% of the workforce in the country relies on small-scale agriculture. Among this, teff accounts for about a quarter of the total cereal production, and it is alone grown by 6.2 million farmers. This makes it the major staple food grain for over 50 million Ethiopian people. In terms of crop production, it stands third, after maize and wheat, by 18.57% coverage of the crop production, which equals to 29.9 million quintals. But due to the traditional methods employed to harvest, the country did not get the most out of it. From the ploughing stage to the threshing process, harvesting is done using conventional techniques. Threshing is done using animals, livestock, walking on it or beating the plant on the ground. This process is primitive, inefficient, unhygienic, and time-consuming. There is 12% to 25% of teff post-harvest losses using these techniques. Due to this, one of the biggest challenges facing the agricultural sector in Ethiopia right now is meeting the growing demand for teff to feed its increasing population. To challenge the primitive way of teff harvesting, modern technologies need to be employed, and that is why this paper focuses on the design and validation of a tangential teff threshing and separation system. By keeping the size variances similar, the design of teff tangential threshing and separation system is validated in comparison with a published research. The threshing rate parameter, the threshing efficiency, and the separation efficiency are the major threshing performance indices that are selected for validation. The validation was done at a threshing drum speed of 27 m/s, threshing drum diameter of 0.48 m, threshing drum length of 0.83 m, wet basis teff moisture content of 12%, Teff MOG bulk density of 35 kg/m3, and Mog throughput, feed rate, of 0.13 kg/s. The result showed 5.4% error in the threshing rate parameter and 1.23% error in the threshing efficiency, while 1.17% error in the separation efficiency at a drum speed of 1200 rpm and feed rate of 275 kg/s. Keywords: teff threshing machine, tangential threshing. 1. Introduction. Teff, Irogrostis teff, is an ancient tropical cereal that has its center of origin and diversity in the northern Ethiopian highlands, from where it is believed to have been domesticated. 1. In Ethiopia, 70% of the workforce relies on small-scale agriculture. Among this, teff accounts for about a quarter of the total cereal production, and it is alone grown by 6.2 million farmers. 2. 3. This makes it the major staple food grain for over 50 million Ethiopian people. It is indigenous to the country and is a part of the culture, tradition, and food security of the people. 4. 5. Teff is a minor cereal crop worldwide, though it is spread in South Africa, Kenya, USA, Brazil, Canada, Australia, and small areas in Japan. 6. 7. Whereas in Ethiopia, it is a major food grain, mainly used to make injera, a traditional fermented pancake. In fact, it is the foremost crop that it is grown on about 3 million hectares annually. 8, which equates to 27% of the land. It is Ethiopia's most significant crop, not only by area planted but also by the value of production, and it is the second largest cash crop, after coffee, generating almost $500 million income per year for local farmers. 9. In terms of crop production, it stands third, after maize and wheat, by 18.57% coverage of the crop production, which equals to 29.9 million quintals. 5. Its production in Ethiopia experienced an average growth of 11.28% per year between 2004 and 2011 and shows no sign of slowing. 9. The price of teff tripled in 5 years to 855.8 bear per quintal in 2010, and it tripled again in 9 years to 2,400 bear per quintal in 2018, and now it ranges from 4,000 to 5,000 bear. Teff is possibly the smallest cereal grain with an average length of 1.17 mm and average width of 0.61 mm. 1000 grain weighs around 0.14 grams 10. It is made of 77.6% carbohydrate, 12.9% protein, and the rest constitutes minerals, fat, fiber and ash. 11. Other than the fact that very little knowledge is known about its nutritional composition and health benefits, the technological limitations in processing teff is the main reason for its consumption not too widespread globally as it is used in its center of origin. However, Kebrebeal noted that, over the past decade, the recognition that teff is gluten-free has spurred global research interest. Health benefits like it reduces iron deficiency, celiac disease, and it prevents and controls diabetes are the other reasons that prompted the researchers. Among the various varieties of teff grain, Concave is regarded as the variety with greater yield per unit of field and easily adaptable, which helps in sustaining food security. 12. 13. With this amount of fascinating facts and figures, teff farming is still done using traditional methods. For this widely used cereal, from the ploughing stage to the threshing process, harvesting is done using conventional methods which dated back when teff was first introduced to the country. For sickling, extensive manpower is used and threshing is done using animals, livestock, walking on it or beating the plant on the ground. Traditional method of threshing are very slow, gives low output, the cost of operation is high and there is a huge loss of grains because of rodents, birds, insects, wind, and untimely rain and fire hazards. 3, 5, 8, 9. 14. Threshing operation and its subsequent loss followed is among points requiring proper attention and that generally accounts about 6% cereal crops loss in Ethiopia. According to the African Post-Harvest Losses Information System, post-harvest losses for teff were estimated to be 12.3%, which is really a big number. More than 12 quintal out of 100 is a loss which can feed a mid-sized family for 2 to 3 years. Other literatures studied that the threshing and other subsequent losses ranges from 12% to 25%. 15-18. This kind of fact is devastating for a country trying to reach food security. One way to tackle this kind of issue is to employ technology-based agriculture, one of which is using threshing systems. Modern teff harvesting technologies will help to transform the arduous, unsanitary, and inefficient harvesting process into a new level. To get the most out of teff, an increase in productivity is required apart from the household consumption. This way it is possible to feed the emerging grain processing industries resulted from the change in lifestyle and the recently burgeoning global teff market, which will boost the economy directly or indirectly. From achieving food security to substituting imported foods, it has a lot to contribute to the growing economy of the country. Other than the economical aspect, using modern technologies like teff threshing systems has its own social impacts which can be pronged in 3. Creating more prosperous communities, more education opportunities, and healthier grain production. Firstly, the teff thresher boosts teff production, increasing agricultural prosperity and self-sustainability and reducing poverty. The product will also spur the formation of local micro-businesses that sell the machines or provide services for other farmers. Secondly, it will prevent children from being removed from school during harvest periods. And thirdly, it will produce a safer, more hygienic grain, improving the health of a majority of the population in Ethiopia. 2. Materials and methods. A teff thresher is a machine that will thresh or detach grains out of the straw mat and sends the threshed teff grain to the cleaning system for further cleaning and separation while the rest of MOG is flowed to the exit. So the main purpose of the machine is to detach, separate and clean teff grains from the straw mat. In this way we can understand that the machine has different systems to form a complete threshing machine. The feeding system, the threshing system, the separation system and the cleaning system are all the major systems that comprises a teff threshing machine. This paper focuses on the design and validation of a teff threshing and separation system. 2.1 Design considerations. The threshing machine is based on a tangential flow threshing system. It incorporates a tangential feeding system, a tangential threshing unit, a tangential separation unit, an extra straw walker separation system and a grain conveying system. First, Teff material is fed to the feeding system manually. Then, a threshing unit consists of active elements like rasp bar mounted on a threshing drum are rotated to drug Teff materials tangentially towards the threshing space. In the threshing space, due to the friction and impact of active elements such as rasp bar and concave bar shown in figure 2.1, Teff grain is detached from the straw mat and flows to the cleaning unit through the concave openings. The concave will be designed in such a way to facilitate a tangential and smooth flow of materials towards the subsequent unit. While the portion of detached grains flows to the cleaning shoe, the rest of material move towards the separation unit for separation of grains and straw mat. 2.2 Working Principle. First, an operator feeds Teff straw and mog to the hopper, leading the feed material to flow to the threshing unit. The threshing system contains a threshing drum, a rasp bar and a concave. When the feed material flows through the threshing space, the space between the lower tip of the rasp bar on the threshing drum and the upper tip of the concave, at a specific feeding velocity, the rotating threshing drum with mounted rasp bar detaches Teff grains. This is due to the friction and impact of the rasp bar and concave grate that wraps the drum underneath at a specific angle. The threshing space or concave clearance has a relatively wider space at the inlet of the material than at the exit. This increases the threshing action and results somehow a compressed straw mat to flow to the next stage. The detached grain will then pass through the concave opening while unseparated grain and the rest of the mog flows to the separation unit. The separation unit has two separation systems, a separator and a straw walker. In the separator, there is a rotating separation drum with mounted bucket-like structures across the edges and a separation concave. The separation drum separates detached Teff grains that are segregated in the straw mat, mog, which came from the threshing unit. Since the separator and concave has a similar structure and arrangement with the threshing unit, it serves as additional threshing mechanism for the unthreshed crop material that flows through this unit. After the Teff grains are separated and detached, it passes through the separation concave openings while the mog, straw mat, is delivered to the last separation stage, the straw walkers. The straw walker serves as another separation unit where the last bit of Teff grain gets separated, limiting the probability of detached and unseparated grains to exit the machine as a discharge. The straw walker unit contains 3 independent straw walkers or shakers which are positioned along the length of the threshing drum length. Each straw walker is constructed from a sheet metal sidewalls of sawtooth profile, to push the straw to the rear side, and steps of screens. The walkers or shakers are mounted on a crank axle on the front and end sides at different angle. The screens on the shakers are inclined at a certain angle, 10220, to form a series of cascades. When the crank rotates, each straw walker reciprocates at different phase in a way when one moves up the other moves down. This motion intensifies the separation action while forcing the mog to the rear side. The separated Teff grain will pass through the screens to the straw walker sieve and then to the cleaning unit while the mog flows to the rear and discharged at the exit. The cleaning unit is the last stage of operation before Teff grains are conveyed to the storage. It comprises an oscillating grain pan, 2-stage of cleaning sieve mounted one above the other, a straw walker sieve and a radial flow fan that blows current of air from the bottom to the upward and rear direction of the sieves. The function of the cleaning unit is to separate free Teff grains from grain chaff and straw mixture, to forward cleaned grains to the auger and discharging mog fragments to the ground due to the action of the fan and the reciprocating motion of the cleaning unit crank. Teff grains, chaffs, small straws, and mog fragments separated from the threshing unit, the separator and the straw walker are delivered to the oscillating grain pan and the straw walker sieve through the threshing concave, separator concave, and straw walker screens respectively. Then, as the result of the winnowing action of the grain pan, the straw walker sieve and the simultaneous effect of the fan, primary grain cleaning occurs since there is a space for Teff materials before reaching the top sieve from the grain pan and straw walker sieve. Secondary grain cleaning happens due to the combination of the oscillatory motion of the top sieve and gravitational force while air is blown from the bottom. Finally, teff grain flows to the bottom sieve through the openings of the top sieve for further and deep cleaning. Again, from the force generated from the vibratory motion of the bottom sieve and gravity, the final cleaning occurs and the cleaned grain flows to an inclined sheet surface where it is conveyed to the feeding auger, which feeds to the storage while the rest of the material is discharged to the exit. 2.3 Mathematical Modeling of teff threshing Performance Indices. For the modeling of the systems, the following parameters were considered. Teff material to be processed is homogeneous and uniformly distributed. Threshing unit is feed with constant feed rate and amount. Effective teff threshing starts at the entrance of the threshing zone. Material to be threshed moves continuously in the threshing space. Mass of the material is continuously distributed in the threshing space. Threshing performance evaluates the working conditions of the threshing system using various indices like Mog Feed Rate, percentage of threshed, unthreshed, separated and unseparated grain, grain damage, cleaning efficiency, specific power consumption and output capacity. Since this paper focuses on threshing and separation system of a teff thresher, the threshing and separation performance indices are discussed below. To analyze teff threshing performance indices, consider the physical properties of teff grain and chaff in the following table. 2.3.1 Mog Feed Rate. The threshing space between the threshing drum and the threshing concave as shown in figure 2.1 has a capacity of consuming more teff straws based on the designed intake volume of the machine. Mog feed rate or throughput is calculated considering teff straw and grain weight, feeding velocity, concave clearance, and threshing drum width and speed. Teff has different varieties across the country and their straw or the plant height ranges between 450 mm to 900 mm. The teff threshing machine should be designed to process the highest straw height. From Table 3.6, the maximum value of the straw diameter in all cases is 1.88 mm. This means the threshing drum along the length of the threshing drum can house specified number of straws if the straw lay one next to another in a series. But this should consider the space needed so that no clogging occurs. Therefore the mass of Mog throughput Qm is expressed as. Now the material throughput or Mog feed rate Qp can be determined based on the above equations. The Mog throughput is the product of the total mass of the Mog throughput Qm and the number of rounds of total straw N processed per unit time. Therefore, Qp becomes Qp equals Qmx N, 2.4, where N number of rounds of total straw processed per unit time, S1. 2.3.2% of threshed and separated teff grain in the threshing drum. The detachment of grains or generally a threshing system is described in terms of probabilistic laws as an exponentially distribution function. The probability density function PDF of an exponential distribution function determines the probability of the grain to detach from the ear/straw considering variables like the concave length and threshing rate parameter 20, 21. For the threshing and separation unit analysis discussed in the following paragraphs, refer to figure 2.1 to identify the terms used. The PDF expresses the probability of grains to be detached or the percentage of threshed grain GT, X, along the concave length 22, 23. It is mathematically expressed as wet basis maximum Mog moisture content represents the wet basis moisture content that results minimum grain damage at the Mog throughput Qp. Optimum working threshing drum speed V corresponds to the maximum threshing drum peripheral speed that result higher grain separation. In this case V will be same as Vc since it is the only selected working drum speed and let be 12% since it is the ideal working moisture content for minimum grain damage and using data studied by Gedikade Merriam 24, the Mog bulk density of teff straw is 35 kg/m3 at a moisture content of 15.1%. 2.4.1 Mog feed rate. According to the listed parameters above and equations discussed in section 2.3.1, the Mog feed rate for the designed machine is calculated as follows. From table 3.6, the maximum value of the straw diameter in all cases is 1.88 mm. This means the threshing drum along its 700 mm length can house 372 number of straws if it lay one next to another in a series. But considering the space needed so that no clogging occurs, let us assume the straw diameter to be 3 mm, which will result 230 number of straws. On the other hand, the concave inlet clearance is 20 mm, which means it can hold 5 number of straws considering 3 mm of straw diameter. Therefore, multiplying 230 by 6, the threshing space can house a total number of 1,150 straws, straw with grain, at a time. As teff crop height is taken to be 900 mm and the feeding velocity is defined to be 0.9 m/s, the threshing drum receives 1,150 individual teff straw every second. Though the concave wraps the threshing drum at an angle of 120, let us consider the threshing drum discharges the straws every half revolution, 1,800, to the next zone, which is the separation drum, assuming the slippage between the crop material and the rasp bars. This means the first round of feed materials will stay in the threshing drum for only half of the revolution. From researches, each straw of teff holds minimum of 500 number of teff grains. With this data and values from considering affordability and design simplicity, manual feeding of teff material is chosen at a feeding velocity of 0.9 m/s. This value can be changed to a higher value to match the threshing drum peripheral speed, 10.6 m/s, so that larger amount of MOG is processed. If the feeding velocity is increased to 2.7 m/s, the mass of MOG throughput increases drastically to 2.54 kg/s or 9.1 ton/hr, since the number of rounds of straw processed per unit time increases to 3. This requires a powered feeding mechanism like screw or conveyor method, though it will increase the cost of the machine, questioning the machine's affordability to the majority of farmers. Multiplying 350 number straws with 8, assuming the inlet concave clearance space, 20 mm, holds 8 number of straws, the optimum number of straws would be 2,800. Using equation 2.26-2.29 results in optimum working MOG throughput Q of 2.05 kg/s, but due to extra factors like human operator incapability and slippage between straws and rasp bar, consider an optimum throughput of 0.53 kg/s. Since the design teff thresher is manually fed, the MOG throughput or feed rate is dependent on the operator. So consider minimum feed rate of 0.14 kg/s to be realistic and analyze worst case scenario. Therefore, the percentage of separated grain at the end of the straw walker SW is 98.11%. This implies 98.11% of the separation losses are recovered, teff grains are separated, in the straw walker. 2.4.5 Model-based threshing and separation efficiency. The threshing and separation efficiency is one of the major performance indices that indicates the teff thresher performance to thresh and separate teff MOG throughput. These efficiencies are determined from the performance indices analyzed earlier. The threshing efficiency is defined as the ability of the machine to detach teff grains from the MOG throughput, whereas the separation efficiency is the machine's capability to separate teff grains that were threshed but segregated in the straw mat. These tasks are done by the actions of the threshing drum, the separation drum and the straw walker in a continuous MOG flow. Threshing efficiency is calculated from the individual threshing capacities in the threshing and separation units. The probability of threshed grain in the threshing and separation unit is 90.25% and 84.32% respectively, as indicated in equation 2.36 and 2.43. This means 84.32% of the threshing drum threshing loss, 9.75%, is rethreshed in the separator. Therefore, the overall model-based threshing efficiency T of the teff threshing machine becomes 3. Result and discussion. 3.1 Validation of design threshing and separation systems. The design teff threshing and separation system is evaluated and validated in comparison with a developed teff thresher designed by Gedekadane Merriam 24. Evaluation of threshing performance indices of the newly designed system is done in comparisons with Gedekadane Merriam S24 design, a PhD thesis submitted to Addis Ababa University and a paper published by International Journal of Engineering. Volume 17 N03, May 2019. He evaluated and compared his design with another existing thresher, Bayer DAR modified SG2000 thresher. As far as concerned with the validation, in order to eliminate different results due to size variance, the size of major components of the threshing units are kept similar with Gedekadane Merriam S design. The threshing rate parameter, the threshing efficiency and the separation efficiency are among the major threshing performance indices that are selected to compare with Gedekadane Merriam S design for validation. For validation purpose, the following threshing drum and teff crop physical parameters are changed to new values which are exactly the same with Gedekadane Merriam S design so that comparison is done on similar basis. Threshing drum speed, peripheral velocity, VC equals 27 m/s. Threshing drum diameter D equals 480 mm. Wet basis moisture content of teff U equals 12%. Mog, teff straw, bulk density equals 35 kg/m3. Threshing drum length LD equals 830 mm. Mog throughput, feed rate, QP equals 0.13 kg/s. The above independent parameters are taken from Gedekadane Merriam S design which are kept similar for both designs that are going to determine the threshing performance indices listed in the above paragraph. If the values of this performance indices according to the newly designed model are similar with Gedekadane Merriam's model or the error is within 15%, then this research will be validated. But if the error exceeds more than 15%, the newly designed model needs to be analyzed again till the error is below 15%. In the following sections, major threshing performance indices are compared with Gedekadane Merriam S design. 3.1.3 Separation efficiency. According to Gedekadane Merriam S design, the separation efficiency is evaluated at different configurations of feed rate and drum speed. His design considers threshing drum speeds of 1200 rpm, 1000 rpm, and 900 rpm. For Mog throughput, feed rate, a value of 400 kg/hr, 325 kg/hr and 275 kg/hr is selected and the moisture content is kept constant at 12% 24. With combinations of this variables, the separation efficiency is analyzed. So using the exact values and configurations, below is the separation efficiency analysis for the newly designed teff threshing and separation system. If error between the two designs is below 15%, then the validation process will be on good agreement. The combinations of the independent variables is as follows. Table 3:1, drum speed and feed rate combinations for evaluating separation efficiency 24. So from all the 9 tests for validation, the maximum error is found to be 8.76% at the minimum drum speed and feed rate of all the configurations and the minimum error is found to be 1.17% at the maximum drum speed and minimum feed rate of the variables. With an average error of 4.9%, it can be stated that the new teff thresher design is validated with good agreement. 3.2 Effects of threshing parameters. To deliver a high-performance threshing machine, the effects of different threshing parameters like threshing and separation drum speed, drum diameter, concave clearance, concave length, material throughput, or feed rate and grain moisture content has to be studied on the effects of the performance indices. In the following sections, these parameters and their effect on the threshing performance indices is analyzed. The graphs below are generated by analyzing the relation between the resulted equations of the corresponding indices in the above sections. 3.2.1 Effect of teff threshing drum speed VC on threshing rate parameter. The threshing rate parameter is one of the major parameter that determines the threshing performance and it is affected by many factors. One of which is the threshing drum speed. The threshing rate parameter and the threshing drum speed has an inverse relation at a constant exit concave clearance and teff moisture content. As shown in the graph below, When the threshing drum speed decreases, the threshing rate parameter increases and vice versa. As shown in the figure, the inverse relation is due to the fact that, when the threshing drum speed decreases, teff materials will have more time to stay in the threshing space. This will increase the rate of grain detachment from the straw mat, which basically is the threshing rate parameter. Although, if the threshing drum speed is increased, then the time to stay in the threshing space will decrease, which will result faster movement of materials without complete threshing, which then will reduce the threshing rate parameter. In a relation shown in the graph, when VC is increased from 300 rpm, 7.06 m/s, to 350 rpm, 8.24 m/s, is reduced by 3.4% from 5.43 m1 to 5.24 m1. When VC is increased from 400 rpm, 9.42 m/s, to 500 rpm, 11.78 m/s, is decreased by 10.37% from 5.02 m1 to 4.49 m1. The following table shows the value of, at different values of threshing drum speed within the range 300 rpm to 600 rpm. 3.2.2 Effect of exit concave clearance on the threshing rate parameter. The exit concave clearance is crucial to the threshing performance indices. Directly or indirectly, all the threshing performance indices are dependent on the exit concave clearance. If the exit clearance is 0, no material will flow to the subsequent unit, leading no work at all. And if clearance is very wide, all the straw mat will flow out without adequate grain detachment, resulting low performance indices. This effect on the threshing rate parameter at a constant threshing drum speed and moisture content is well described in the figure below. As shown in the figure, there is an exponential relation between threshing rate parameter and exit concave clearance. When the clearance is wider, because there will be more material flow, the rate of grain detachment increases until it reaches a maximum. When the exit clearance is reduced, since there will not be more material flow, the rate of teff grain detachment or the threshing rate parameter is reduced significantly. When E is increased from 4 mm to 6 mm, increases by 19.7% from 3.89 m1 to 4.35 m1. The value of, at various values of exit concave clearance is shown in the table below. 3.2.3 Effect of current concave position on the probability of threshed teff grain. In the above section, the current concave position and the probability of threshed grain at a constant moisture content, threshing drum speed and Mog throughput is related as GT, x, equals 1e.x equals 1e 4.75x. Figure 3.3 below shows the relation between the probability of threshed grain and the current position of the concave length or threshing space length. At the beginning of the threshing space length, the probability of threshed grain is 0 since no material enters the threshing space yet. The maximum probability of threshed grain is found at the end of the threshing space length where the materials exit the threshing unit. At the middle of the threshing space length, that is when teff materials travel 50% of the threshing space length, 69.5% of teff grains from the input amount are threshed. It can be shown that the longer the concave length, threshing space length, the higher the probability of teff grain detachment. The following table shows the percentage of threshed grain at different concave positions. The comparison between the probability of threshed and unthreshed teff grain along the threshing space length is shown in the figure below. As shown in the figure, at the beginning of the threshing space length, the probability of unthreshed teff grain is 100% since there is no material yet. But this value reduces along the threshing space length and it gets its threshing loss 9.25% at the end of the concave length where teff material exits the threshing unit. 3.2.4 Effects of Mog throughput, feed rate, on threshing efficiency. The effect of feed rate on the threshing efficiency in the threshing drum is described in the figure 4.5 below. When the feed rate is increased from 0.14 kg/s to 0.26 kg/s, the threshing efficiency drops by 2.2% from 90.28% to 88.29%. This is because the sudden increase in feed rate will clog the threshing space, limiting the flow of crop materials. In this case, some portion of the crop will be segregated in the straw mat, which will remain undetached from the straw. When the feed rate reaches 0.5 kg/s, the threshing efficiency in the threshing drum increases by 3.2% from 88.29% to 91.22%. This is due to the fact that after few revolutions of the threshing drum, the clogged straw will leave the threshing space, allowing more impact on the straw mat. The effect of feed rate at constant drum speed on the threshing rate parameter lambda and threshing efficiency is shown in figure 3.6. As it can be shown, the change in the threshing rate parameter due to feed rate has a small impact in the threshing efficiency. 3.2.5 Effects of MOG throughput, feed rate, on separation efficiency. The effect of MOG throughput on separation rate parameter and separation efficiency is shown in figure 3.7. Due to the same reason as the threshing efficiency, the straw clogging due to feed rate will reduce the efficiency at first, but after drum develops continuous inertia, the clog will break, which in turn increases the separation efficiency. In general, the separation efficiency increases by 0.8% when the feed rate is increased from 0.14 kg/s to 0.5 kg/s. 3.2.6 Relations of separation efficiency. Separation loss over the concave length. The separation efficiency has a maximum value at the beginning of the concave and reduces to a certain value at the end of the separation space, as shown in figure 3.8. On the other hand, the separation loss is zero at the concave inlet and it reaches the maximum value at the concave exit. This is due to the fact that at the concave inlet, there is no material inlet yet, hence there is no separation loss. But as the separation space advances to the concave exit, the separation loss increases to its maximum value 14.12%, as shown in figure 3.9. Figure 3.8 Relations of separation efficiency over the concave length. At the concave inlet, since there is no material inlet, unseparated grain is zero, which means the separation efficiency is 100%. But as the concave length advances, unseparated grain will increase while the separation efficiency is decreased. At the end of the concave, the separation efficiency reaches 85.76%. At 45% of the concave length, the separation efficiency is 88.08%. So the separation efficiency drops 2.6% after half of the concave length. Figure 3.9 Relations of separation loss over the concave length. At the middle of the concave length, that is when the straw mat advances 0.225 m, the separation loss is 12.49%. So in the remaining half of the concave length, the separation loss increases only 1.63% to reach 14.12%. To compare the separation efficiency and the separation loss, their relation over the concave length is shown in figure 3.10. Figure 3.10 Relations of separation efficiency and loss over concave length. 3.2.7 Effects of drum speed on separation efficiency. The effect of drum speed is proportional to the separation efficiency. Increasing the drum speed will increase the separation efficiency at the cost of grain damage. Because over a certain drum speed, the impact of separation drum will be high, resulting in grain damage. As shown in figure 3.11, when drum peripheral speed is increased from 10.6 m/s to 21.2 m/s, the separation efficiency increases by 2% from 85.9% to 87.42%. Figure 3.11 Effects of drum speed on separation efficiency. 3.2.7 Power consumption. The effect of drum speed on drum power consumption is shown in figure 3.12. The relations shows, an increase in drum speed from the input power source will increase the power requirement. When the drum speed is increased from 450 rpm to 650 rpm, the power consumption increases by 6.28% from 6.38 kilowatts to 17.2 kilowatts. Figure 3.12 Effect of drum speed on drum power consumption. 4. Conclusion and recommendation. 4.1 Conclusion and recommendation. From this research work, the following conclusions were drawn. The Mog Feed Rate, the threshing efficiency, separation efficiency in the threshing drum, separation drum, and in the straw walker is determined. The performance of the threshing unit is validated with a thresher designed and prototyped by Kebrebeal, which is based on another model, and the result shows the maximum and minimum separation efficiency error between the two studies were 8.76% and 1.17% respectively. Hence, all the performance indices mathematical functions were validated with experimental data obtained from Kebrebeal's design. The evaluation was analyzed with various configurations of threshing drum speed and Mog feed rates. The drum speed used was 900 rpm, 1000 rpm, and 1200 rpm, whereas the Mog feed rate used was 275 kg/s, 325 kg/s and 400 kg/s. The error generated between the two studies on the threshing rate parameter was determined to be 5.4%. The designed model illustrates the relations of threshing parameters like drum speed, Mog feed rate, moisture content, concave clearance, and concave length with performance indices. The percentage of threshed grain in the threshing drum and in the separation drum is 90.25 and 84.32% respectively. The percentage of separated grain in the threshing space, separation space, and straw walker is 85.88%, 85.69 and 98.11% respectively. The above performance indices at different sections of the machine defines the Teff threshing machine's overall threshing efficiency to be 98.47% and the overall separation efficiency to be 99.96%. Any related research in the future should consider the value of portability and the country's landscape for agricultural activities so that the end users can move from field to field easily. When designing or using a Teff thresher, the appropriate moisture content of the Teff should be noted. High moisture content will increase difficulties during Mog flow and very low moisture content will increase grain damage. The inlet and exit concave clearances are crucial during designing and operation of the machine.